This is Mr. T with the tutorial on solving systems of equations using matrices. In our last unit we talked about solving systems of equations algebraically, and we, if you remember, had two methods for solving systems of equations. One where we used what's called linear combinations, and second method was called substitution method. This first example problem we have here would be easy to solve using linear combinations. We could multiply this equation number 1 here by 2 and add the equations together. The x's would disappear and we could then solve the equation. If we look at a more complicated system, this system has 3 variables, x, y, and z. Therefore, we need 3 equations. We could also solve this one using linear combinations, but the process is much more tedious and involved and very error-prone. I'm not even going to go through that for you here, but the basic concept would be to say take these 2 equations, say multiplying this equation by 2 and adding those equations together, getting rid of the y, so we would get a new equation with x and z. And then we would do the same thing with this pair of equations, say multiplying this by -3, and we would get a second equation with x and z. So now we have 2 new equations with only 2 variables, and we would proceed and solve those using either substitution or linear combinations. And then once we found our first variable, we would start backtracking through all those equations and using substitution to find all 3 of our variables. You can just imagine, with as difficult as that was for me to explain, actually doing that would be quite time consuming. So we have another method for solving the equations. So let's go back to our simpler system here and talk about this. Now we can represent this equation or system of equations using matrices. So if I take a matrix, our first matrix here, we're going to fill in and we're going to pick the coefficients of the x's and the y's. I'm sorry, in the second x. And here we're going to take our y coefficients. We are going to make a matrix which is our variables. It'll be a column matrix. And then the right side of our equation. Now this representation as a matrix equation is equivalent to this, and we can show that just by reviewing our matrix multiplication. Remember, if we wanted to multiply these 2 matrices, we take a row from the first matrix and multiply it times a column. So if we did that, we would get 3x plus 2y. And then we can take our, that wasn't supposed to move, but you get the point. We can take our second row times that column, and we would get negative 6x minus 3y, and that equals 6 and negative 6. And if you remember, on matrix equivalency, we take corresponding entries, so 3x plus 2y would have to equal 6. Negative 6x minus 3y equals negative 6. So I've just shown that this matrix equation here is equivalent to our system. Let me clean this up. Okay, in our last video, we talked about solving systems of, matrix equations. If we represent, this is our coefficient matrix, let's call that matrix A. And this is our variable matrix, we'll call it matrix X. And our right side equation, our right side values of the matrix, we'll call that matrix B. And if you remember from our video on solving matrix equations using inverse matrices, we want to get rid of this A here, so I would need to multiply by A inverse, the inverse matrix of A. So I have to do the same thing to the other side of the equation, and remember, matrix multiplication is not commutative, so I have to put the A inverse in the same relative position as I did over here, so on the left. This gives us the identity matrix, And over here we haven't computed what that is yet. We'll do that in a minute. And the identity matrix times x gives us the x matrix. And the x matrix is going to be a column matrix with the variables of x and y in the entries. So now we're going to use the graphing calculator to solve this problem. So I'm going to enter this into A and this into B. And I'm going to enter that, I'm going to pause here and enter that, and then we'll come back here in a second. Okay, now I'm back. And we can see here I've entered into matrix A our coefficient matrix, and I've entered into matrix B our right side of the equation. So what we just showed here, to find our variable matrix, we need to multiply by A inverse. So matrix 1, remember, x inverse times matrix B. And we get here our solution, x being -2 and y being 6. So our solution to this system is the xy pair of -2, 6. Now let's do this same thing with the more complicated equation we had here. So our coefficient matrix, matrix A, will be 3, 2, and 4. 2, -1, 3, and 5, -3, 5. Again, we have our variable matrix, and we have our right side. So this is the matrix equivalent of our system, and again we've got the same pattern. So when we use systems of equations using matrices, we're always going to have this type of equation, so we know from before, I'm not going to redo that matrix math, that our solution will be A inverse times B. So let me pause again here and enter our values in the calculator. Okay, you can see now that I have entered our coefficient matrix and our right side matrix, and again we want to calculate A inverse times B, so let's do that. And we have our solution here of x being -3, y being 2, and z being 4. So again, that's x, y, and z. And if we took those numbers and put them into each of these equations, we could verify that this is a solution to all three equations. Now this is fairly easy to do. It was no harder here other than a little bit more data entry of solving a 3x3 system as it was a 2x2, and it would extend to be equally easy if we had an equation with 4 variables and a system with 4 variables and 4 equations. Now this is made possible by having a graphing calculator that can do our inverse matrices. If we had to do this back in my day where we did these inverses by hand, then this method was still easier in many cases than solving it algebraically, but was still quite tedious. So you're lucky with our technology. So good luck as you apply these yourself.